Hello students, this is Dr. Abelia and we are starting the plate tectonics module. You want to log in to learn.concord.org and enter your information. You can do it through Google, you can do it through Schoology, hit run by myself, and you should end up at activity 1. I ended up at a different activity because I've been working on this. We're going to use GPS data to learn how the Earth's surface is broken into many moving pieces called tectonic plates. We're going to use a model called Tectonic Explorer. It's a data model to look at the different plates and their edges, look at earthquake and volcano data, and some paleographic maps. Let's get started. So it shows a picture of Earth from space. The large brown and green landmass is Africa. Antarctica can be seen at the bottom of the image, covered in snow and ice. So this is Earth. Has Earth always looked like this? Will Earth continue to look like this in the future? In this module, you use the evidence to make predictions about how Earth might look in 500 million years. Question 1. How do you think the Earth might look in 500 million years? This is just you doing your best on the information that you have right now, previous science classes, intuition, logic, evidence. Explain your answer. Why do you think what is going to happen is going to happen? What supports your prediction? Why did you make your prediction? There are no right answers here. We just want to see what you're thinking about. So here's GPS. You might have GPS on your phone, or maybe somebody who's driving you around has it in their car. The turn-by-turn directions depend on GPS. GPS technology is also used in stations positioned around the globe. GPS station data provides information about how places on Earth are moving relative to each other, because those tectonic plates that we live on are always moving. And we can find out how fast they're moving in which direction using GPS. Some of the GPS station data are shown on the map below. GPS stations are only placed on land because GPS signals don't go through water. So things are moving underwater as well. We just can't detect that with GPS. Signals won't reach underwater. It's hard to feel that the ground is moving when you're standing on it. GPS satellites send information to GPS stations, which provide us with measurements of how much Earth's surface is moving from the orbit. The green dots show the original position. So this GPS started here, this GPS started here, this GPS started here. The yellow lines point in the direction that each station is moving. So this station is moving that way. These stations above Africa here all seem to be moving that way. South America doesn't seem to be moving very fast, but Africa looks like it's moving up to the right-hand corner of this map here in the northwest direction. A longer line means faster movement than a shorter line. So it looks like Australia is really booking it in geologic terms compared to South America. Are all of the GPS stations moving in the same direction? Well, we can compare to Australia and Africa to the west coast of the United States. These are moving roughly northwest, and these are moving roughly northeast. So you can use that to support your answers for question 3 and question 4. Compare Australia to the west coast of North America. Based on GPS data, show the Earth's surface is moving very slowly, only millimeters per year, just a little bit faster than your fingernails grow. Even so, if given enough time, actually a little bit slower than your fingernails grow. Even so, if given enough time, Earth is 4.5 billion years old. Slow movements can cause big changes. Based on today's GPS readings, we can make predictions about where continents were in the past. Where do you think Africa was located 10 million years ago? We are noting that it's moving this way up to the right-hand corner of the map. Where was it before it was here? We probably think that it was lower and to the left. Since it's moving up to the right, in the past, it's probably moving down to the left. And that can support your answer for number 5 and number 6. Right now, it's moving up to the right, so northeast. It probably was considerably more southwest earlier in geologic time. Volcanoes and earthquakes. In addition to GPS data, geologists also use data about earthquakes and volcanoes to help them understand how Earth works. When we have earthquakes and volcanoes, it's a signal to us that plates are moving, there's an edge of a plate, and things are dynamic in that particular part of the Earth's surface. Tectonic Explorer is a tool that visualizes volcano and earthquake data by mapping it onto Earth's surface. So we can make maps of where all the earthquakes and volcanoes are. The volcano data are already shown on the map as triangles. To visualize the earthquake data, press the Start button. The earthquakes will be displayed on the map in the order in which they occur. Use the timeline to see the dates of the earthquakes. To hide the earthquakes or volcano data, so you can focus on one at a time, click Data Type in the menu and uncheck the feature that you don't want to use. If you lose your place, click the recentering icon. So here's the key. Let's look at that. So we're going to have different earthquakes, different colors of earthquake data based on their depth. Blue is the deepest, red is the shallowest. The magnitude of the earthquake will be represented by the size of the dot. And the volcanoes go from active in white to darker, means they erupted a long time ago. So let's add some data here. We want volcanic eruptions. So that's going to be already. And then we're going to show the earthquakes as they happen here. Let's watch the earthquakes appear. And you're probably going to notice that the volcanoes and the earthquakes kind of line up in the same spaces. We can kind of see there's a whole bunch of activity along this line and along this line. Over here, a lot is going on. There's a lot of volcanoes going on here and here as well. I recommend watching the videos called Ring of Fire in the folder for this. So I've already taken a snapshot and circled where I see the lines of both volcanoes and earthquakes in the same place. You can do a better job than I did. I left some more for you to work on over here. So please take your own snapshot and draw on. We can replace the snapshot here. If you want to draw on your snapshot, you can pick a color here. I'm going to pick white because that seems to show up the best. And then you can just draw where you see lines of volcanoes and earthquakes. And I noted in my drawing that I think these lines represent plate boundaries. And you can finish the rest of this drawing here. What did you notice about the lines of earthquakes and volcanoes and where they seem to occur on Earth's surface? Well, they seem to occur in the same place, and they seem to occur in particular places in very discrete lines. So I'll give you some hints here on writing your answer. Volcanoes and earthquakes. Same places. Distinct or discrete lines. That is not the answer, but it'll give you some clues on how to write your answer. What are your initial ideas about why earthquakes and volcanoes happen in lines? Well, if you watch the Ring of Fire video, there's a couple good Ring of Fire videos on YouTube by Crash Course Geology and Vox. The Ring of Fire occurs here, and then if it's all around the Pacific Ocean and here. And if you watch those videos, which are in our Schoology folder, or you can find them on YouTube, you'll have a pretty good idea about what the Ring of Fire is and what that means in terms of volcanoes and earthquakes lining up in a particular place. On the previous page, use Seismic Explorer to view patterns of earthquakes and volcanoes on Earth. Next, we're going to take a look at a model that uses scientific principles to help us better understand the dynamics of Earth. It's called Tectonic Explorer, and we kind of get to create our own planet here and crash the tectonic plates into each other and see what happens. And we can take cross sections. It's pretty fun. It's an Earth-like planet with moving pieces that are made up of continents and ocean. We want you to explore a little with the model and see what you notice about the way the pieces interact with each other. Press Start to play the model. You can rotate the model to see different sides. So we can rotate this. This one's got a few continents on it already. Later, you'll be able to put on your own continents. So the model, once you set it up, will play, and you can see the plates move. You can see some mountains being built here, because I can see the elevation here. 8,000 meters is pretty tall, and that means it's probably mountains. Some more mountains are being built here. There are probably some islands appearing here, island chains. There's more mountains here. It's kind of cool to watch things evolve in well, not real time. This is modeled time, but we can speed time up and watch what happens. So what changes to the planet's surface do you see as the model runs? Well, we talked about the mountains appearing. We talked about some island chains appearing. It looks like kind of a new ocean is developing here. It's kind of growing. These planets are being pulled apart. So they were together and now they're apart. So those are some ideas about what you could write. You could talk about mountains, islands, new ocean. That's not the answer, obviously, but those are some good sentence starters or some like good word bank. Question 11. Describe what happens when two pieces of the surface are moving towards each other. Well, let's go find where that's happening. I know these two pieces are moving towards each other because there are mountains being built as the two plates slam into each other. So those mountains will probably continue to build as the model rolls on here. You can watch on your own time. Describe what happens when two pieces of the surface are moving away from each other. Let's go see if we can find that somewhere. There we go. That crack right in the middle there. You can tell they're moving away. It's just creating a little bit of a ridge across the bottom of the ocean. We can tell it's a little bit shallower because it's lighter blue. And that's seafloor spreading, if you know what that is. Otherwise, you can look it up. So I can see a little bit of seafloor spreading. I can see a little bit of a ridge right in the middle here, right by my arrow. It's lighter blue, so I know that that seafloor is rising a bit, and I can see that their plates are moving apart. GPS data, along with earthquakes and volcanic data, allow scientists to make a model of what Earth looked like in the past. So this is Earth in the past. The maps below illustrate the locations of Earth's continents and oceans over hundreds of millions of years. So we're going to see what happens over hundreds of millions of years. There are 15 maps representing Earth from today, that's 0 millions of years ago, to 514 million years ago, or MA or MYA. Click through the slideshow to see how Earth's surface changed over the past 514 million years. Note the locations of land masses throughout the series. Also note how the location and size of oceans and seas changed over time. So this is a good thing if we're trying to project what the Earth is going to look like in 500 million years. It's kind of good to go back 500 million years and look at what happened in the past to predict what's going to happen in the future. So let's click back. Let's watch and see what's happening to the continents. Pay attention to South America and Africa. They're all kind of getting smushed together. So the Earth's surface is always moving. It's very dynamic. Start with the late Jurassic map, 152 million years ago, and move forward in time. Describe how South America and Africa move compared to each other. So we need to go to 152 million years ago. There we go. So we see South America, we see Africa. And remember how we looked at the GPS data and we saw that Africa is still moving up to the right, north, west, and South America is just barely moving in the opposite direction. So let's watch what happens. And there we go. You can run it backward and forward a couple times to get a better idea of what's going on. So describe how South America, right here, and Africa moved compared to each other. So you might want to go backward and then go forward in time and look at that again to get a better description. What happened to the South Atlantic Ocean over the same time period? So focus right in here at the South Atlantic Ocean. Notice just a couple clicks what happened to it. As we go forward in time, what happened to that ocean over time? What do we think about those plates? South America, the South American plate and the African plate, are they going to be moving together? Or are they going to be moving apart? So you can draw your own conclusion there. And when you're ready to upload your answer, You're going to go to the Show All Answers page. On your iPad, there's going to be a little icon. So here's a screenshot of an iPad. You're going to see this little square with an up arrow. You're going to click that. You're going to click Options, choose PDF, and then find Notability and click the Notability icon. That will appear about right here. So click this little square with the arrow, choose Options, choose PDF, and then find the Notability icon that will appear and upload it to Notability. Make sure you have Activity 1 and Activity 2 in Notability before you turn it into Schoology. Thank you so much. This is Dr. Robelia signing off on Activity 1 of What Will the Earth Look Like in 500 million years. Thanks so much.